Physics Notes, Unit 26, Vision and Optical Instruments. One of the most incredible devices on this planet and related to the human body is the human eye. It's incredible. We're going to discuss the physics of this and other optical instruments, but most of you biology people can probably tell me way more about the eye than I could tell you, but we're going to study the physics part of like how it forms images and so forth, because it has to do with lenses and refraction and so forth. But you know, our discussion here is probably not even going to be like 1% of what we know about eyes. They're an incredibly designed piece of machinery or detector. The amount of information that goes into your eye every second is incredible. What it does to process information and send it to the brain, it's beyond our comprehension. I mean, we can understand a lot of things, and we're going to understand things, and we keep learning more things, but you know, it's just mind-boggling what the eye can do and what it processes. So, having said that, here's an image that I pulled up recently from an online search. There's a lot of words in here I don't even understand. You don't need to understand all these words. Maybe you guys do, because if you're a biology person, if you're pre-med especially, you probably have to know a lot about the eye. Obviously, you know, the eye has a lot to do with ophthalmology and opticians and making eyeglasses and doing laser surgery and other things like that for correcting vision. And some of you might be on that particular track of study, so you know, you're going to want to pay close attention, like always, to this particular lesson. But incredible, even every little piece of the eye, from the lens to the cornea to the optic nerve to the retina to the iris and the pupil. That's the only thing that's not on this diagram. Well, not the only thing that's not on this diagram, but the pupil, the opening that's in the middle of the iris. The iris is the colored part of your eye, but the pupil basically is the hole that, you know, is controlled by muscles. When it's dark out, it opens that pupil up larger, and when it's bright out, it closes down that aperture, that hole, to let less light through your lens. And then this back part here, it's yellow in this diagram, is where the images are formed, and it's your screen for an image. The whole thing, it's called the retina, and the middle part, it's not on here, it's called the fovea, I think. Fovea, F-O-V-E-A. And we'll talk about rods and cones as well. They're not labeled here. We'll talk about those separately in a little bit. And then there's, well, vitreous humor. This is the vitreous body, the kind of the watery stuff that's inside your eye, and all kinds of things. And once again, this is only a partial list. It's incredible what's going on here. But now let's talk about the physics of the eye. So here we go. It has to do with lenses. Okay, so some important terms, concepts, and relationships. One thing that's important when we study the physics of the eyes is called the near point, the closest point for which you can focus images. For good vision, basically for young people or healthy eyes, your near point is 25 centimeters. In other words, if you get closer than that, it's hard to focus. Some people who have really, really good eyes can focus on things that are even closer than 25 centimeters without glasses, without contact lenses, without correction, like jewelers and things like that. People who have to look at really, really small things, watchmakers in the olden days, or they have to use some kind of magnifying glass to help themselves out. We'll do some calculations on this in a little bit. But bottom line is also near point. People, when they get older, their near point is no longer as near. It gets further and further away. That's why you see, you know, older people like myself having to hold things further and further from their face, because their near point is not so near. It's a little bit farther. We'll talk about that. We'll talk about correcting that. Your far point, once again, healthy eye, in general, it's infinity. You can see things at infinity. Now, once again, you can't focus on things that are too small, far away. And here's another thing about vision. You know, how far away can you see? Well, you basically can see infinitely far. I mean, for example, the moon. How far away is the moon? Well, the moon's like 230-some thousand miles. You can see it, because vision is not the act of something coming out of your eyes. It's something going into your eyes. And there's certainly light from the moon, especially at night, that you can detect coming into your eyes. Or the sun, 93 million miles away. And the other stars, which are light years away. So you can see infinitely far, in a sense. And if the object's big enough, you can actually make out some details. Okay, now, another thing is when we start doing the computations, d sub I, that's the image distance. So in a standard size eye, That's the distance from your lens in your eye to your retina. Once again, your retina is not flat, it's curved. That's another miracle of the eye. It's forming an image on a screen, a real image that's flipped upside down, by the way. Then your brain flips it right side up. It's a whole other incredible thing. The more you think about this, and I think that's what's cool about science in general, whether it's biology or physics or chemistry, or even any other subject, history, English, whatever you want to study, if you really are dedicated to studying that subject, you'll find that it becomes more and more intricate and interesting the deeper you go. And you'll get questions answered, but as you answer questions, you end up with more questions. That's the inquisitive mind. All right, but anyways, I'm off track there. Retina. It's the screen in the back of your eye. Real image. You get a real image inverted because you have a converging lens in your eye. Back on your retina, you have rods and cones. Rods are the detectors. There's like a couple 100 million of these things in the back of each eye that basically detect light intensity. The cones have quite a bit of its different structure, and the cones are mostly in like the middle of the back of your eye in the fovea area. And there's like 6 million of those, not as many by far. The rods, there's 100 times, no, not 100 times as many, 50, 40 times as many, 30 times as many. But the cones detect the colors. That's what gives you the color vision. We'll talk more about that later. The optic nerve, it gives you like a blind spot in your eyes, which you don't really notice because the other eye compensates for the blind spot in each eye, but that's where all the information goes from the rods and cones to the nervous system, or whatever you call those connections that go to your brain that then interpret what you're looking at. Once again, it's mind-boggling how much information is going to your brain every millisecond because of what's going into your eyes. Those two little holes. Okay, cornea, all right, that's the front transparent cover on the front of the eye. It actually does more bending of light than the actual lens. It's responsible for about 2/3 of the focusing power of your eye. And that's what's reshaped in laser or LASIK surgery. That's what they shave to reshape to then correct your vision. They don't mess with your lens for LASIK surgery. So then you have your lens. It's convex. You'll see a picture. Well, you saw a picture of that up there. And it can be changed in shape for different, when you look at near items, it has to have a greater power to focus on things that are close as opposed to things that are further away. We'll talk about that. Like I say, your D sub I is 2.00 centimeters. It's fixed. D sub O changes. If you look at things far away, D sub O is basically infinite. And then your near point is usually around 25 centimeters. You can't get much better than that. But F has to change. So you have muscles that stretch out your lens, okay, or so forth. But when you're looking at things that are far away, that's usually your relaxed position. It takes more eye strain to look at things closer. That's when the muscles have to be active to change the lens, the shape of the lens. And that ability to change the focal length is called accommodation. Once again, if you're looking at something closer, you need to have a smaller focal length for the greater power, smaller focal length for the lens, which means it's going to be thicker. Yet the muscles have to make it fatter in the middle than it was, and then when it's looking at something far out, which is called the relaxed position, it's actually thinner in the middle. And the thing is, there's not that much difference really. So we usually refer to near vision as accommodated because that's when the muscles have to be active, and then when you're looking at something far away, that's called relaxed, or if you're looking at something infinitely far away or sufficiently far away, it's called totally relaxed. And usually there's about an 8% difference between the focal length or the power of the lens when it's looking at something far away versus something that's close together. We'll calculate that here in a few minutes. So it's not that much difference, but it's enough difference so that allows you, once again, an incredibly designed instrument that can focus on things that are near and far, and it changes between those two in just a flash, unlike cameras and things like that. We've kind of figured cameras out and telescopes and lenses, but microscopes, but the eye, there's nothing that compares to the eye as far as its ability to accommodate, change its focal length, and process information and have information input and make sense of it. Visual acuity is a term we use for the ability to see detail, see things sharply and in focus. Once again, our greatest visual acuity is in the fovea, the center part of the back of the eye. We have 20/20. What does that mean? 20/20 vision. That's normal vision. It means that you can see at 20 feet with detail what the normal healthy eye can see at 20 feet. So 20/30 means you don't have as good a vision. Okay, so at 20 feet, you can only see the details that a normal person can see at 30 feet. So if you're looking at something at 20 feet away, somebody with good eyes can see the same detail on something that's further away, 30 feet away. And likewise, like 20/60 means somebody looking at something at 60 feet away, they would see it in clear detail. All right, you would have to have that same object 20 feet away to see that same detail. Now it's even possible to have better than normal vision. 20/10 vision means that if the normal person is looking at something at 10 feet, all right, you can see that object as clear as they can. At 10 feet, you can see that same object at 20 feet. So you can see it in detail at further away than they can. All right, so that's a quick overview of 20/20 vision and so forth. But here's some review of some of the equations, and we're going to make some slight adjustments. Well, not adjustments, but some review of these. So we have our lens equation, 1 over d sub O object plus 1 over d sub I equals 1 over f, and p equals 1 over f. In this unit, it's going to be advantageous to put everything in meters. And since p equals 1 over f, if I take this 1 over f right here and plug it in and just rearrange that, it's going to be advantageous to put those together and just write this equation like this: lens power equals 1 over d sub 0 plus 1 over d sub I. That's putting those two together. So that's going to be advantageous to use the lens equation in that fashion. Okay, so I probably should have circled p. I'm putting in p for 1 over f. I'm putting in p for 1 over f. Now magnification, there's two equations: negative d sub I over d sub O, or, and I use capital M, and the book uses lowercase m, doesn't matter, h sub I over h sub O. If you put those two together, it's going to be useful to have negative d sub I over d sub O equals h sub I over h sub O. So you're going to see me use that equation. It's not really anything new. Nothing there is really new, but it's probably better to put these equations in this form. It's going to be a little bit more useful. All right, so here we go. This is kind of showing you the idea of how an object, in this case it's at a near point, that's part B basically, and it's showing you how the image of the lens and the cornea and so forth, actually it turns out that there's a lot of bending here. Basically each layer, and even different layers of the lens, it bends the light a little bit differently. So it's not just one bend, it's not just the one bend here, but we show one bend as it goes into the cornea here from the outside. So, and then there's this other layer, which I don't even know what it's called. I think it's somewhat liquidy there, but forget the name of that fluid that's in there. But there's bending as it goes through all these different layers. But the net result is you get a real inverted image. So as we do these problems, there's going to be basically 4 types of problems. I mean, there really is only 2 equations per se, those equations that I just circled. But conceptually, we have to think about these. When we do problems without corrective lenses, those tend to be the easy ones, where you're going to have your near point or your far point, and it's pretty straightforward. So like this is going to be a pretty straightforward problem. It's 2 parts to it. When you get corrective lenses, it gets a little bit more difficult. But for example, here it says a good person with 20/20 vision, find the typical lens power. So part A, it's pretty straightforward. I mean, the equation is P equals 1 over d sub O plus 1 over d sub I. That says 1 plus. Okay. So the power here, if you're looking at something very far away and you're a typical healthy eye person with no corrective lenses, so you're looking at something that's infinitely far away, all right, what is the power of your eye? Because you can focus clearly. Now, d sub I, we're using d sub I right here in all cases for these non-corrective lenses. We don't have corrective lenses on. Now that's 0.02 meters. 2 centimeters is 0.20 meters. So you're gonna have power equals, well, basically 0 plus 1 over 0.02 is 50. 1 over infinity is 0. So the power of your eye for a healthy person is 50 diopters. That's a capital D there. Well, I'll spell it out. That's supposed to be a capital, but capital D is all you need. that first number there is 50, but diopters, D-I-O-P-T-E-R-S. But it only works out if you start off in meters. So that's the power of the eye in the relaxed, it's in a totally relaxed mode. All right, where you're not really using muscles per se, it's relaxed. Part B, what is the power when you're looking at something at your near point, the closest you can focus on for a normal healthy eye? Well, once again, I'm just going to plug into that equation. So it's just going to be P equals, now my object is at the 25 centimeter mark, 0.25 meters. It's at the near point. That's where my object is. My image still has to focus on the retina, 2 centimeters behind the eyeball. So that's what this is saying here. Basically, this is 2 centimeters, 2.0 centimeters, 0.02 meters. So now the power, 1 over 0.25 is 4.0 plus 50, not 0.0. I'm adding sig figs this time. I could have said that in the first one, 50.0 as well. But that comes out to be 54. I'll just go back to 2 sig figs. 54 diopters, capital D. Okay, so that's basically the extreme to which you would change the power of your eye by using the muscles of your eye to make the lens fatter when you're looking at something closer. So if you look at these two numbers, that power increased by 4 out of 50. That's 8% increase. In other words, 4 out of 50 is an 8% accommodation. ACCOMMODATION. Okay, I'm off the page there. Whoops, sorry. An 8% accommodation. 8% increase in power. That's what a healthy eye basically can do. And if your eye's not healthy or strong enough, maybe you can only do a 4% or 6%. Or if you have good eyes, a 10% accommodation. You can change it even more because your near point's even closer than 0.25 meters, 25 centimeters. All right, so once again, when there's not corrective lenses, it's pretty much a straight plug into those equations or that equation, and I'll do a few more of those in a few minutes here. But what about this one? What's the height of an image on the retina of like a dot, like a period on a piece of paper, which is a really small dot, 1.26 times 10 to the negative second centimeter dot. What's the diameter of that dot on a piece of paper if you hold it 55 centimeters from your eye? Okay, that's not that far away, like about 1.5 feet. So once again, d sub I is 2 centimeters. I'm gonna use the other equation now. Negative d sub I over d sub O equals h sub I over h sub O. So it's just a plug-in. So the image distance has to be negative 2.00. The object is 55. Now, okay, as long as you stay in centimeters here, everything's in centimeters. It'll come out in centimeters. These are ratios. So I didn't have to go to meters here. So this is the one exception where I can do this in meters. Don't have to have centimeters. 55.0. That's my object distance. And it says height of the image. That's what we're looking for. Height of the image, h sub I. If the object has a size, diameter of 1.26 times 10 to the negative second centimeters. Those are all centimeters. So the centimeters cancel out. The answer will come out in centimeters. Bottom line is I would cross multiply the 1.26 times the 2 and then divide by 55. So the height of the image, you can go to your calculator pretty easily with this. The height of the image is going to be negative 4.6. Negative 4.6 times 10 to the negative 4th centimeters, because we were in centimeters. Really small. That's the height of the image upside down. The negative means it's upside down on your retina. And once again, that's really, really small. But you have detectors back there that make sense out of all this. I mean, your cones and rods are even smaller than this. Quite a bit smaller than this, I believe. So I don't know how many rods and cones are being hit by this particular light from this particular object. But many of them are, and then send information to your brain to tell you see this thing. And it's a really small dot. But it's incredible, once again, that I guess most people can see that at that distance, especially if you have normal eyes or you have corrective lenses. All right, so now we have problems with the eyes. We have myopia, nearsightedness, which is what most people have when they're young if you wear glasses or contacts. In other words, things that are far away are blurred. So you're nearsighted, you can see things near. It's a very common condition. So you can't focus on distant objects. In other words, your far point is not infinite. All right? And you need diverging lenses to fix this. You'll see that in the diagram below here. So then we have hyperopia, farsightedness. That means you can see far but not near. It's not as common in young people. So that's when you have a blurred image for something that's close. It's because the image is focused, the eyes are causing the light to focus behind the retina. I forgot to mention that in myopia. That the image is actually being focused, the lens is too strong. It's focusing the light in front of the lens, or the eyeball, the eye cavity is not, it's too big for the focus. But I think it's usually a problem with the lens focusing too strongly. The focus is in front of the retina. So hyperopia is the focus behind the lens, or the retina. So that's corrected with converging lenses. And I skipped this part where it says the near point is more than 25 centimeters. Okay, so you have to hold things further away to see things because you can't see near. Presbyopia is basically the same thing as hyperopia. It's just basically though a condition that happens when you age, because your lenses can't focus anymore. They start to degrade, so you need what are called reading glasses. But it's the same basic fix as hyperopia. You need converging lenses. It's basically the same problem as hyperopia. So here's hyperopia, where the focus, this dashed line shows you behind the retina. The front surface is the retina. So for example, this is supposed to be on the retina right here, on the surface of the retina. All right, or they're showing you a converging lens, which is usually the disc-shaped lens. It's fat in the middle. Converging lens helps you focus the light onto the proper spot. So that's the reading glasses for older people or younger people who have hyperopia that need those kinds of lenses to fix that. Once again, not that common. As opposed to myopia, then you need diverging lenses, the ones that are thin in the middle, because your focal point before the lenses is too strong or it's too short. It's not hitting the lens surface or the retina surface, the screen. So you get fuzzy. Okay, all the problems give you fuzzy images. So you have a diverging lens that spreads the light out a little bit and moves the focal point back a little bit, and you get proper focus and corrective lenses. And we've figured this out. I don't know. Well, now we figured it out with either glasses and frames or with contact lenses, or we fix it by reshaping the cornea with LASIK surgery. But we've had reading glasses around for what, 200 or 300, or glasses in general for 200 or 300 years. So here's an example of somebody who's nearsighted, who has myopia. We need to fix this with a diverging lens. And these are the problems that become a little bit more challenging. It's not, you have to think a little bit more deeply. We still will be using the equation power equals 1 over d sub O plus 1 over d sub I. Just as kind of a refresher, this person has a far point of 35 centimeters, which means that's as far as they can see clearly, but beyond 35 centimeters, things are fuzzy. They can't see out to infinity. For example, I could have asked you this, like a sub-question would have been, what is the power of their lenses in that particular situation? So for example, this is not being posed here, but if you just plug that in for your, instead of infinity like we did in problem number 1, if we plug in 0.35 as their far point, as far as they can see, and you have to focus still on the lens. So this is without correction right now. This is what this person's power would be without the corrective lens. This is always going to be 0.02 without corrective lenses. With corrective lenses, we're going to be changing some numbers there. But bottom line, 1 over 0.35 is 2.9, and then 2.9 plus 50 is 52.9 diopters. That's the power of their lens in this case. So they can't adjust their lens to what is needed to see, far. 50 diopters, what you need to see infinitely far, clear, or great distance without corrective lenses. So we need some help here. So we need a diverging lens. So here's where it gets a little tricky. What you need your lens to do is you need the lens. So forget your eye right now. So this equation right now, well, the one we just did applied to your eye without glasses. This right here now, actually in the actual problem, we want to apply this equation to the lens itself. So apply it to the lens, not your eye. Apply to the lens only. And I'm just saying that loosely because obviously that lens is in front of your eye. What you need to do in these problems, if you're talking about correcting farsightedness, nearsightedness, myopia, what you want to do, and it's really not that hard once you get the pattern here, is you want the lens to actually to form an image such that that image is out, or that the object would be apparently coming from infinity, and the image, okay, the image needs to be, in this case, at your far point. So that image right there, that little tree right there, the image needs to be at 35 centimeters. 35 centimeters from your eye. You need to put that at your far point. So that the lens then will basically make it appear like it was coming from infinitely far away. Well, bottom line is the lens with glasses, and if there's contact lenses, you don't even need to make this adjustment. With contact lenses, and this is not the scale, this tells you it's 1.5 centimeters. So obviously this is not the scale. That's 1.5 centimeters. So this distance here is 33.5 centimeters. Okay, and it looks smaller than it is on the diagram because the diagram is not the scale. But bottom line, what this means is that lens that's in front of your eye needs to put an image from the lens itself at a distance of 33.5 or 0.335 meters from that lens. And it's got to be that's a negative, because that's a negative image. It's upright, it's virtual, it's a virtual image in front of the lens, so it's got to be negative. So bottom line, you have an object at infinity. You have an object at infinity, or way out there, that tree is way out there, relative to this lens that we're using to correct our vision, such that that lens forms an image, a virtual image, at the far point for your eye. And then your eye will make an image of that image that will be sharp and clear. All right, so if you do the math here, this person then needs corrective lenses that have a power of negative 3.0 diopters, a diverging lens with that power. So bottom line is, you can take some shortcuts here. You can always put the infinite symbol here if you're trying to correct for nearsightedness, myopia with diverging lenses. All right, now we have a person who's farsighted, hyperopia. We need to correct for that with a converging lens, as you see in a diagram. Before I do that, once again, something you didn't need to do here, but I did it anyway, just to show you without corrective lenses. This is without the corrective lenses over here. The power of this person's eye, because they can clearly focus on something that's 90 centimeters away, but nothing closer than that. That's their near point. So if something's at the near point, if we have an object at the near point, 0.90 meters away, your image distance still has to be focused on the retina behind the lens, 2 centimeters. So that's 50 plus 1.1. The power of the eye in that case is 51.1. But for some reason, because of the inability of the muscles to control the lens or whatever, cannot produce a power of what we need. We need a power of like 54. Actually, no, 50. I think it's just 50. No, 54. I think it was 54. That's what it was. If you go back to, I think, problem number 1. But this lens, this person cannot, their eye cannot go to a power of 54. So we need help. We need a converging lens to help us with that. So once again, now we're going to apply the lens equation. P equals 1 over d sub O plus 1 over d sub I. So this equation, though, has to apply to the lens, not to the eyeball. Here, the diagram will help us at the bottom here. In the previous problem, when we were correcting for the nearsightedness, the actual object that we're looking at, that tree was infinitely far out. So whenever you're doing a correction for that with a lens, diverging lens, you will put in, the infinitely far distance. But for this one, okay, we want the object, which will be the same every time, we want the object 25 centimeters from. So instead of infinity, we want 25, except for we got to make one little adjustment there, because you have to measure from the lens, and the lens is not right by the eye. In other words, let me draw this out. The object right now is 25 centimeters from my eye. 25 centimeters. That says 25 centimeters. But it's not 25 centimeters from the lens, because this distance is 1.5, not to scale. 1.5 centimeters. So if you do the math here, that is 33.5. That's how far the actual object is from the actual lens that's going to correct for our vision here. So when I plug in the equation, it's going to be 1 over 0.33. No, it's not 3. That should be a 2, not 0.33. It's 0.235. 0.235. I did the wrong math there. Sorry about that. It's 0.235. Sorry about that mistake. You probably caught that, I hope. 0.235, because 25 take away 1.5 is 0.235, not 33.5. In the other problem, the previous one, we didn't need to subtract that distance because infinitely far, whether you subtract 1.5 doesn't make any difference. So you didn't need to factor that into the object distance in the previous problem. But here we did, or do. So same thing for the second part of this now, the image. We need to figure out how far this image is from the lens. Well, this distance here is 1.5 centimeters. And what the idea here is, we want to put the image at the far point. Okay, in the previous problem, we needed to put the image at the person's near point. At the person's near point. Here we're putting the image at the person's far point, and the person's far point here is 90 centimeters. And so the distance, though, from the lens is what, 88.5? That's 88.5 centimeters. So that's what I have to put into the equation. I'm going to switch back to red, though. So that's 1 over 0.885. So that's the tricky part about this. Bottom line is, if you have your glasses always 1.5 centimeters from your face, however, which is typical, if there's contact lenses, you just put in the 0.25 right there, because the contact lens is right on your eye. There's a problem like that in the homework. You just put in 0.25 because you don't have to subtract the 1.5. The contact lens is right on your cornea. All right, but you put the image, that lens will create an image at the person's their near point in this case. In the previous problem, you had to put the image at the far point. So you do the math here. Oh, and one more thing before I make another mistake. It's a virtual image. It's a virtual image in front of the lens, so this has to be negative down here. Sorry about that. I made a couple mistakes there, but I think I've overcome the mistakes. That's got to be negative. It's a virtual upright image. Virtual images are always negative. It's on the same side as the object, so we have to factor that in. Very important. And if you do the math there, 4.26 plus a negative 1.13 gives you a positive 3.13 diopters. This is a converging lens, so it has to come out be positive. In the previous one, it was a diverging lens. It had to come out negative, which it did. So that's correcting for farsightedness, hyperopia. You put in the near point, or the 0.25 with a small correction for the lens distance from your eye, and then put in your actual far point for the person measured from the lens, though. Once again, if you're a contact lens, if it's a contacts, you would just put the negative 0.90 in there. It's always going to be negative. It's going to be a virtual image. So back to a problem that's just talking about the person's eye. Now we're kind of doing a backwards problem. They're giving you the power of the person's lens. It's not 54, which would be a near point of 25 centimeters, but it's just a straight plug into the power equation. Power is 1 over d sub O plus 1 over d sub I. All right, so you have 52.8 diopters, which are the correct units, 52.8. Okay, it's 52.8 equals, okay, at what distance is your object that you can see clearly if it's going to put an image on your retina 0.02 meters. That's your image distance. That's what your lens does from your lens to your retina for these problems that you're just applying the eyeball, the lens in your eye. It's always 0.02. So you do the math there, you get 52.8 equals 1 over d sub O plus 50. So you end up with 1 over d sub O equals 2.8. So d sub O is 0.36 meters, 0.36 meters. So they have a near point of 36 centimeters. So in other words, anything closer than that they can't reach. So they got to hold things far out, or you have to have corrective lenses, like we did in the previous problem. All right, number 6, person who is nearsighted. Okay, they have a far point. Oh, it's not a very good far point at all. 8 centimeters. Anything beyond 8 centimeters, that's really bad. By how many diopters should the power of his eye be reduced? So using laser correction vision. Okay, so once again, we're just going to go, you plug into the equation straight up, and we're applying this right to the eye. No corrective lenses yet. The power, we have a far point. So we're going to put in the far point here. If an object is at the far point, 0.08 meters, it's going to properly focus on the retina at 2 centimeters. So it's 1 over 0.08, which is 12.5 plus 50.0. So the power rate now of the eye without any help is 62.5. 62.5 diopters. Now that's not the answer for good vision. For good vision. Okay, the far point, the power for far point power. You can look back at problem number 1. The power was, I think, 50 diopters. Okay. For good far point power, if the image is at infinity, the object is at infinity, your lens has a power of 50. So by how many diopters should the power of his eye be reduced? Well, 62.5 minus 50. So 62.5 minus 50.0. It's a reduction of 12.5 diopters. So they have ways that they can then control that with the laser when they, because the laser is very, very precise. They cut a little slit in your cornea and they reshape the cornea, and they take a little bit off, and you can read more in detail about that. I'll talk more about it later, but basically you got to reduce the power by 12.5 diopters. Okay, if a person has a far point of 55.5 centimeters, 8% ability to accommodate, what is the closest object you can see clearly? Once again, this is pretty much a straight plug-in to the equation. P equals 1 over d sub O plus 1 over d sub I. But it's a couple step problems. They have a far point, so that's a faraway object. So they can see a faraway object 0.55 plus 1 over 0.02. You're using your eye is just without a corrective lens. So if you do the math here, all right, so I went through and did this. I did this whole problem. They have a far point of 55 centimeters. I'm over here on the left. So you have 1 over, put an object at that far point. Can't see any farther than that. You're focusing on the retina, 0.02 meters. So you get 1.8 plus 50.0. So your far point, the power for your lens for the far point is 51.8 diopters. Now it says they can accommodate by 8%. So they can change their power by 8%. They can increase it by 8%. So I'm taking the 51.8 right here and multiplying by 1.08. That's an 8% increase. I could have just multiplied by 0.08 and added it on, but it's faster just to multiply by 1.08. When you multiply by 1.08, you're increasing the number by 8%. So the near point power is 55.9 diopters. So now I plug that into the equation once again. If I have my near point power of 55.9, all right, you're still going to focus it on your retina at 2 centimeters. So you have 55.9 equals 1 over d sub o plus 50. Subtract the 50 from both sides, you get 1 over d sub o is 5.9. So this near point here is 0.17 meters. 17 centimeters is better than normal. That's kind of like the situation I'm in. I have a hard time seeing far. Okay, I'm nearsighted, but my near point is closer than 25 centimeters. I can see better with my glasses off, and it's close. So I'm kind of unusual like that. I guess what I should say, I can see better. With my glasses off, I can see things close real well, clearly without my glasses on. I still need them to see far. I need to get rid of some of this. Now, number 8 and 9 are tricky because, once again, we're back to corrective lenses. So contact lenses. So, just be careful. We have to apply this to the lens. We have a lens prescription. So, the equation is P equals 1 over d sub O plus 1 over d sub I. Whenever you're trying to apply the power equation to a corrective lens for the far point, okay, for the far point, you want the image to be at that far point for the lens, okay? We're not talking about the eye now. We're applying this equation to the lens itself. So the power is negative 3.5. Okay, I think you can go back and look at, which problem was that one? Yeah, it was problem number 3, where we were correcting for nearsightedness, myopia. So, okay, so this is equal to, so the rule is, all right, you want the object relative to the lens to be infinitely far from the lens, plus 1 over d sub I. This will give us the distance to the lens. So this all applies to the lens. However, now that the lens is on your eye, this also applies to the eye because the lens is on the eye. So bottom line is negative 3.5, that's a negative 3.5, equals 0 plus 1 over d sub I. So 1 over d sub I is negative 3.5, so take the reciprocal of that, and you get negative 3.0. No, you don't get negative 3.0. You get negative 29, or negative 0.29. Negative 0.29, which is 29 centimeters. So your far point, the far point is 29 centimeters. I mean, it's 29 centimeters in front of, this is meters, 0.29 meters is 29 centimeters, but that's 29 centimeters in front of the lens, which is in front of your face. That's your far point. In other words, anything beyond that you cannot see clearly if you have that particular prescription. Anything closer than that, theoretically, you can still see clearly because you're nearsighted. All right, and finally, correcting again for farsightedness, we have a near point. We want to find the near point for this person with that prescription, and this is a contact lens, so we don't need to make that slight small adjustment, but it's plugging into the power equation relative to the lens and the image and objects measured from the lens, not from the eye and the retina. All right, so we have 1 over d sub I. All right, so we want, the power is 0.650. That's easy. And once again, what we want is the object to be at the standard near point, 25 centimeters. So every time you do these corrective lenses problems, this is always 0.25 or 0.235 if you subtract off the small, if you're using eyeglasses. For contacts, you just put in a 0.25. You want the object of this diverging lens to be, it's a converging lens in this case, to have an object that's at that spot. So then the image location is what we call your near point. So there we go. So every time you do this, like the previous problem number 8, you always put infinity there for the object location. Here we have an object that's 25 centimeters from your face, from your eye, that you want to be able to see clearly, like a normal person. So then the conditions are your image location is, for this lens, is what you can actually accommodate yourself when we do the math here. 0.650 equals 1 over 0.25, which is what that should be. 0. No, it's not 0. It's 4.0. It's 4.0. Oh man, 0. I erased that. 0.25. Okay, that's 4.0. Let me say 0, 0 plus 1 over d sub I. All right. So then we get, all right, 4.00 minus 6.5, which is what, 3.35 equals 1 over d sub I. So that should be negative. D sub I is negative 0.30 meters. Okay. And once again, it's negative, but that's because it's a virtual image. The object is still plus 25 centimeters away, but the image is, well, 30 centimeters away. It's further away. Basically, the object is inside the focal length of this lens. That doesn't matter. But you can say the near point is 30 centimeters. Or you can say 0.30 meters, because that negative means it's a virtual image in front of the lens, and that's how far it is from the lens, which is how far it is from your eye here, because this lens is on your eye. So there we go. We have the miraculous eye, the marvelous eye, the incredible eye, some of its capabilities, but then how to correct for the particular problems using diverging and converging lenses and applying the concepts of lens power, the lens equation. And then we will talk a little bit in the next lesson about some of the other issues with the eye and color perception and so forth. But all of this is fascinating. Stay tuned for the next lesson.